You got it? I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for another week just completed, weekend about to start. Pray be with us today. Help us to understand proofs of these theorems we're going over, and just to prepare the students' hearts and minds for the test, which is upcoming next week, Lord. In your name I pray. Amen. All right, so I see you already gave me your homework. That is good. Sorry about posting the solutions of some of those problems online, But again, there's only so many problems to go around in Gamelin. And I want to assign you the interesting ones, and if I happened to solve them last year, oh well. Anyway, so the story goes is why we probably need to change books next year, or next time I teach it. Whatever happens first. All right, so let me show you an example. Another example, kind of like the last one, but maybe a little bit easier. How about this? I want to calculate the integral around some loop of, goodness gracious, let's say something like cosine of z over z squared plus 4 dz. All right, and I'm gonna not even gonna write the loop just yet. I want to emphasize how would you understand if this is integral around some loop c? How are you gonna do this calculation? Basically, the whole question is where is the integrand singular, right? Where is there a division by 0 in that function? So cosine's harmless, right? Cosine's holomorphic. It's on the whole complex plane. It's an entire function. Its derivative is just minus sine z, right? But z squared plus 4 could be 0, 2 points. What are those 2 points? Yeah, plus or minus 2i. And so here, there's this technique called partial fractions, which says I can rewrite z squared plus 4 as a over z minus 2i plus b over z plus 2i, because z squared plus 4 is equal to z plus 2i times z minus 2i. So there's this general technique of partial fractions which suggests I can rip apart a rational function and write it as a sum of basic rational functions like this. And so basically I just got to figure out what's a and b. So I think a is equal to 1 over 2i, and b is equal to minus 1 over 2i. Is my guess? Just looking at it. Let's see, let's work it out. 1 is equal to a times z plus 2i plus b times z minus 2i. So just to emphasize, this right here was a guess. Let's see if my guess is right. So this is 1 is equal to a plus b times z plus what? Plus 2i times a minus b. So this gives us two equations, right? We get a is equal to minus b, and we get what? How did I get a minus b, by the way? If you differentiate this equation with respect to z, you get a plus b equals 0. So a plus b has to be 0. A is equal to minus b. If I plug in z equals to 0 in this given equation, what do I get? 1 is equal to 2i times a minus b. So I get a minus b is equal to 1 over 2i, right? I guess I can rewrite the last equation as a plus b equals to 0. That might be more useful to me at the moment. So you add these equations, what do you get? 2a is equal to 1 over 2i. Aha, I was wrong. In fact, a is equal to 1 over 4i. Right? And b then is equal to minus 1 over 4i. All right. So this is why you shouldn't guess. This is why you should work things out, right? Or if you make a guess, you have to check it. So checking a guess here amounts to just putting those numbers and cross multiplying. Anyway, so long story short, what we got here is 1 over 4i times 1 over z minus 2i minus 1 over 4i times 1 over z plus 2i, right? Or much more interestingly, if you come back up here, we can break it into two integrals, right? Integral around c, well, let me pull the 1 over 4i up front. 1 over 4i integral around the loop of cosine z over what? Z minus 2i dz minus 1 over 4i integral around the loop that I haven't even specified yet. Although I am assuming something about this loop, aren't I? What am I assuming? It's what? I'm guessing plus or minus 2i is not on the loop, right? What else? That's most of it. Okay, so are we good? Can I erase this? So you did partial fractions in calculus 2 for the sake of integrating rational functions, right? Well, it also has use in integration theory here. So, I mean, there is a decomposition of 1 over z to the fourth plus 1 we looked at last time, plus I, right, was it? I looked at 1 over z to the fourth plus I in the last class. It took us like a half hour to work it out. You could find a partial fractions decomposition for that. Something like a over z minus ghost plus b over z minus dead ghost plus c over z minus stick figure plus z over z minus, what was it, Pac-Man? So those, you could rip it apart into a sum of these four things. And so what's the advantage of doing this algebra? Right. So let's think about let's say C looked like this. All right, and so maybe this was 2i, and so minus 2i's out here. Now the loop C needs to be what? Counterclockwise oriented, right? Well, it does. All of these things are built over Green's theorem at their base, right? And Green's theorem assumes a counterclockwise orientation. Otherwise, there'd be minus signs. I mean, it's not that you can't do it, it's just you got to be careful. And then so what? If that's the loop, if that's the C, how does this integral work out? So if that's the C, then this right here, right, is holomorphic within and near C, right? So that's 0 by Cauchy's theorem. Not the integral theorem, but just plain old Cauchy's theorem, right? And then by Cauchy's integral formula, m equals 0 case, what's this equal to? So here, cosine of z is the f of z, right? Cosine of z, of course, is holomorphic. The singular point is 2i, so we get 1 over 4i times what? 2 pi I cosine of 2i. See, the reason I was making you guys calculate cosines and Cauchys of all kinds of weird values, it wasn't just my intrinsic meanness. Of course, that's part of it. But it's also because I want you to be able to calculate these integrals, right? So i's cancel, and we got what? Pi over 2. And let's see, cosine of 2i is what? Cosh of 2, right? it's fun to stop and think about what real integrals we've just done. This, doing this one complex integral, we're actually doing a pair of real line integrals. What are they? What would this be if you wrote it as real and imaginary parts?
Cosine of x plus iy over x plus iy squared plus 4 times dx plus I dy, which would equal out to something a lot nicer than what I said.
But Michael is exactly right. That's the thing is, right, you're doing this integral over some loop. And yeah, that's what you're going to get is you're going to get integral of nasty stuff. Right, over c plus I times the integral of other yucky stuff. See, so you've done this pair of fantastically complicated line integrals, really, at once by just evaluating complex cosine. It's really powerful, the theory that we're wielding here. It's something. I mean, if you actually, you're looking at like cosine times sine, cosine of x times sine of y over something like, x squared minus y squared plus. It's unpleasant. I mean, it's cosine divided by a quadratic integrated over an arbitrary loop, essentially, that contains this point.
Does great responsibility come with this great power that we've given? You shouldn't ask that.
In fact, yes, great responsibility does come with great power, and that's why we have tests. Yeah, the 30-minute problem. Okay, so I just wanted to give you an example which was slightly less complicated than the one we did last class, so you can see that, in fact, I mean, of course, we could have also approached this the same way we did last class, right, which was just to apply, Cauchy's integral formula with a more complicated f of z, right? If we'd used Cauchy's integral formula, so here, without the partial fractions, our f of z was, cosine of z, right? With partial fractions, right? The way we just did it, right? If I was to do it the way we did last class, you'd have had f of z would have been like, cosine of z divided by what? Divided by z plus 2i, right? And maybe that's easier than doing the partial fractions. It kind of depends on how comfortable you are with partial fractions at this point, right? So you could have also approached it using Cauchy's integral formula, m equals 0, with that more complicated integrand. And you see what would have happened when you plug in z equals to 2i, out pops the 4i. So, I mean, you could probably argue that this is easier to do without partial fractions at the moment. I don't know. I can't decide. All right, so I need to show you some theorems, which are a little bit non-trivial. So I'm going to project them, if you don't mind. Well, I guess even if you minded, I would still do it. But I trust you will mind. Do you guys have an exciting weekend lined up? You're studying for the test? Well, then yes. What's that?
Your quiz.
My quiz. Oh, no.
Oh, just kidding.
Thank you. Thank you, Sharon. I forgot about the quiz.
I ruined everything.
Now we're definitely not buddies. Would you rather have like a 350 point test?
Yeah.
Oh.
You could just give us a post-it credit up.
No, I'll get you. It's important to have a quiz so you guys can.
Also, are we ever going to get the last question back? Just out of curiosity. Yeah, we did. I know what I got on it, though. I think we got that. Yeah, ignoring Michael, I don't think we got it. Oh, he gave it to us at the end of class one day.
You probably ran out because you like biology more.
Yeah, probably.
Thank you, Sharon. I almost forgot about that.
Just give us the quiz you gave them last year along with the solution. That would be really easy.
That would be easy to write. Good idea, Lorenzo.
Because we definitely see in all of our different handwriting.
I love the 126 students when they come up to me. He's like, do you realize that that problem you put on your test was the same as the one you gave last year? I'm like, yeah, that was a gift for those of you who studied. And she's like, oh, I guess.
Do they still think you're Santa?
What's that?
Do they still think you're Santa?
Stop saying right now.
You said you're Santa.
I am Santa. I don't, I don't think they realize how easy I'm being in there. No, not really.
I'll come and tell them.
It won't mean anything to them. They haven't lived your life. They haven't walked a mile in your heels. Your shoes? I don't know. I can't see. Boots? Oh, okay. Let's see here. Where are we? Thank you, Sharon. I really do remind me again at the end of class so I really don't forget.
There'll probably be gags back here.
All right, I'm going to try to go somewhat fast through these because I want to make sure I have a little bit of time to write some more things on the board after this, but not too fast. I do want you to understand them. So on the test, I will hold you responsible for a few proofs. This might be one of them. I'll be more explicit about that once I have a chance to sit and think about my life and about your life and what I should require of you. But this is Morera's theorem. So f of z is a continuous function on domain U if the integral around the boundary of a rectangle is 0, right? For every closed rectangle contained in U with sides parallel to the coordinate axis. So it's saying none of these kind of rectangles, right? They have to be these kind of rectangles, so non-weird rectangles. Then f of z is holomorphic with continuous derivative. You guys understand that the statement that the derivative, the mapping z goes to f prime of z be continuous, that's not the same as holomorphic. Like, we have proved that holomorphic implies continuous, but that's for the function, right? The continuity of the derivative function is a separate item, and this theorem gives it to us. So here's the argument. So you look at a rectangle, all right, and if we have vanishing around rectangular loops, that means that the red path integral has to be equal to the blue path integral, right? By that path independence and loop correspondence that we talked about earlier. And so we can define a primitive, an antiderivative, for f of w by just taking the integral over gamma d of z of f of w. And that definition doesn't make a lot of sense until you see the picture on the next page. So let me just record that definition for the next page discussion. F of z is equal to the integral. I don't think you really need to pan over to this or anything, Sharon. It's okay, you won't. I forget you studied at the Beirut School of Cinematography. It's the maximally non-observant school of. It's like can't make it too easy for the viewer. Like, you have to leave them guessing a little bit. If you just follow what the lecturer is doing, that's too easy for the viewer. You know, we expect more. Okay, so this path gamma d of z, it's a path from x naught to x plus z. So the rectangle I had in the, oh, here it is. So this point right here is x naught plus iy naught. This point up here is x plus iy, all right? Now, so I want to show that f prime of z exists, so I want to consider the difference quotient ultimately. So I consider a small delta z small enough so that it is split as, small enough No. Sorry, that's a different rectangle.
It's a very different rectangle.
Yeah, let me not get distracted by that. We can look at this rectangle nonetheless. I mean, D is... That's fun. Okay, so D is some domain. This rectangle fits inside it, right? And so f of z plus delta z minus f of z would be, the path to z plus delta z minus the path to z. Both of these paths are anchored at z naught, right? So I can, let's see here. So I guess there would be a bigger rectangle you'd think about just from, well, see if I can, I've lost my place, curses. So this step right here, of course, is just that we've reversed the path, right? So that brings this minus inside to be a plus. The gamma d z is, let's see here, where is z in this picture is the frustrating thing. Oh, z is right here, duh. All right, so yeah, I think, man, I should have put this all on one page. I've made my life more difficult than it needs to be. This is actually just kind of a general comment. If you have any rectangle in the domain, you can trade the upper L path through the lower L path. That's probably something we're using on the next page. We can exchange the upper L for the lower L, given the condition, the precondition of the theorem. All right, so z naught's a fixed point. We're defining the big F of z from. And so again, we're looking at f of z plus delta z minus f of z. So this gamma d is a path from z naught to z plus delta z, right? And we can use this lower L path to get there. And then gamma d of z would be this guy, the red path. But the red path is reversed, so it's minus gamma d of z, right? So if you look at this, if I go, look at this, so if I go this way, then all the way up here like that, and then I also have like this, and down here, like that, these paths down here cancel, right? So the red plus the blue is giving you this part of the rectangle. So if you look at these 2 points, it's like you go around this way, or you can go up this way. So what that means is the sum of the red and the blue paths can be replaced by the green path. And the green path is going from z to z plus delta z. All right. So I call it the upper path. All right, so that's most of this proof is really the picture. So, sorry, Michael. So if we look at then gamma u of z plus delta z, we go integrate from z to z plus delta z dw, and you notice that f of z is independent of that integral. So I can pull it out, and I just get the integral of dw from z to z plus delta z, but that just gives you delta z, because that's the displacement of the path. It's kind of neat, right? If you integrate dz over a line segment, what happens if you integrate dx over a to b? You get b minus a, right? You get the displacement between the upper and lower bounds. Same with a complex. If you integrate dz over a line segment, you get, or I guess any curve, you get the displacement of the curve, the final point minus the initial point. But of course, delta z here is actually a two-dimensional vector if you want me to get picky about it. And then of course we have the f of z out front, which just still multiplies. All right, so returning back to the difference and using what we just talked through, we replace the blue and red path with the green path to get this. And I also, so we worked out the middle piece here as being f of z delta z, right? But then what I'm doing here is I'm adding 0 also, right? See that? Added and subtracted f of z there. So, of course, the f of z dw piece we just explained that that gives you f of z delta z. So like this, this right here integrates to that piece, right? And then you're left with, by this calculation right here, and then you're left with f of w minus f of z dw, which I call the star-star equation. All right? Now, what's the length of this path? It's going from z to z plus delta z, right? So I argue that that has to be, certainly the length of that is less than 2 times the length of z. That's very generous. I think I could put a square root of 2 there and still be fine, right? What's the length of a path that's rectangular? If the displacement's like this, certainly this plus that is longer than the length of the direct. So, yep.
What's the sub?
What's the what?
The sub. M equals sub.
Oh, the supremum. So it's the greatest. Let's see what I may say. Let me say it right here. It's larger than all these values, but as small as it can be, and so it's the least upper bound. I would say it's the maximum, but we want the idea that it could be right beyond the values which are actually attained. So we say supremum. Okay, so then you can use the ML theorem, right? And the ML theorem which I didn't prove in class, but maybe I'll make that one of your responsibilities so you learn it. Hey, hey. And it's easier than some of the things I'm going over. You'd probably rather have the responsibility to be able to prove the ML theorem as opposed to prove Morera's theorem.
Yeah.
Okay. Good. That's the reaction I was hoping for.
Make it 3 more errors.
No, ML. We want to prove ML.
I know because we want that. It's probably gonna not.
No, I'm reading Dr. Cook's mind right now.
I think he just doesn't want to grade
Sharon is working on getting you guys to prove Morera's theorem. She's so close to it. My gosh. If I didn't know better, I'd say she's doing it on purpose, but I don't think she is. Let's see here. So the ML theorem gives you this, right? And then if you divide that by delta z, the modulus of delta z, you got the difference quotient. And then you got f of z sitting here. And then where's m coming from? M is what? M is the supremum of this, right? So what happens as delta z goes to 0? As delta z goes to 0, this just goes to a point, which means the difference goes to 0. M goes to 0 as delta z goes to 0, quite intuitively from this. And consequently, we find that the derivative of big F is little f. In other words, f of z is an antiderivative. Right? So f prime of z is equal to f of z by the inequality above. Furthermore, since we assumed that f of z was continuous, we assumed f of z was continuous, hence f prime of z is continuous, right? Because f prime is equal to little f. Consequently, f of z is both holomorphic and possesses continuous derivative f prime of z on d. Then you just apply corollary 4.45 to Cauchy's generalized integral formula. See f prime prime of z is equal to f prime of z exists and is also continuous. So that is why it wasn't bad for us to assume the continuity of the derivative before, even though I hadn't proved it. It follows automatically from this condition, as we see. Questions? Let me go on here. Goursat's theorem. Here's what Goursat's theorem says. It says if f of z is a complex valued function on a domain D such that f prime of z naught is equal to that at each point of D, then f of z is analytic on D. Now this is Gamelin's version. When he defines analytic, he throws in the continuity of the complex derivative, right? So here's how I would state theorem 4.7.1, which I don't think is even numbered in Gamelin. I've added the numbering, right? In our language, the theorem can be stated, if a function is holomorphic on a domain, then the derivative map is continuous. The assignment of z to z prime is continuous. Now, you notice that the assumption of Goursat's theorem is just pointwise differentiability, complex differentiability, right? So the question is, why is it that those assignments as z naught goes to f prime of z naught for each z naught in the domain, why is that a continuous Why is that automatically a continuous assignment? So the proof is kind of neat. What you do is we were going to use Morera's theorem, and we'll take a closed rectangle. I can't speak. With sides parallel to the coordinate axis, you divide the rectangle into 4 identical subrectangles. All right, and then you pick one of the subrectangles to be the one for which the integral around that rectangle of f of z dz is the largest. All right. So it then stands to reason that the integral around the largest one has to be greater than or equal to 1/4 of the integral around the super rectangle, the big rectangle. Does that make sense? If I take something, I divide it into 4 rectangles, and I say that R1 is the value of the integral around the subrectangle which is largest, then if I take, and if I add, if I take 4 times that, it has to be larger than the integral around the whole rectangle, right? I mean, just that's logical. And then you take the subrectangle and you divide it into 4 subrectangles, and you pick the integral around that subrectangle, which is largest. You call that one R2. Then it stands to reason that that one is going to be, if you take 4 times that, it's larger than the integral around R1. Right? What do we do next? Again, and then you take that subrectangle and divide it into 4 subrectangles, and then you pick the integral around the subrectangle there, which is largest. And in so doing, you end up with eventually this estimate that the integral around the largest rectangle is less than or equal to 4n times the integral around the nth subrectangle. Now, if you're like me, that didn't make a lot of sense. It'd probably be good to look at this picture. This kind of argument I'm giving you is generally known as a Cantor process argument. This is one of many such arguments that you'll encounter in mathematics. But so here's the big rectangle. I'm just supposing that's the one around the integral which is largest. And then that is the one that's largest in that in terms of integrals around rectangles, and then so forth and so on and so on and so on. And that's as far as I could get in paint. So
And that's the proof there, right?
that is.
We just draw the picture.
Well, if I was to ask Goursat's theorem on the test, that would mean that we had a master's program here, at least, maybe more, I don't know. I mean, no, I don't think this is a reasonable thing to ask undergraduates to prove in an hour test. I mean, if you asked me to do it from memory, I'd actually have to prepare.
Okay.
I have prepared for this, but, even so, I don't know. I guess if you're left on a desert island, you have some incentive, maybe you could do it. I don't know. Anyway, as n goes to infinity, it's clear the nested rectangles converge to some point. Now there we're using some kind of extra complex analysis idea, right? But it seems like a reasonable idea, doesn't it? If you have this nested sequence of subsets, each one inside the other, they should converge to some point if they're always getting smaller. But anyway, the length of the perimeter of R is L over 2 to the n. What's L? L is the length of... so L is the perimeter of R, the original rectangle. Do you see why the subrectangles have L over 2? Like the first one. Let's see, if this has perimeter L, what would the perimeter of this one be? If you take this rectangle, right, and you kind of just take the lower half and then put it over here, you can see it gives you half the perimeter of the larger rectangle.
So 1/4 L.
1/2 L. The perimeter halves. It doesn't quarter.
Sorry.
I know I wanted to say quarter too, but as you can see, if you just look at the first one, you can see it already. Just take this, imagine taking this L and just like move it over and flip it over so you get, so the yellow box gives you this much of the green box perimeter. Okay, so then, what do I say here? So as f of z is complex differentiable, what's that mean? That means that you can make the difference of quotient minus the value of the derivative as small as you like, right? For z close enough to the limit point z naught, right? So I can choose an epsilon sub n For each one of these, I can choose an epsilon sub n such that this is less than epsilon sub n. Hence, I have that the difference of f of z and f of z naught minus, basically f of z minus the linearization is less than epsilon times the difference between the modulus of z minus z naught. But of course, that is less than or equal to 2 epsilon L divided by 2n. Why would that be? The difference between z and z naught is, z and z naught, z naught, I guess, is that point, right? And let's see here. That's just a statement about the distance between z and the center point. Try to see here. I'm not sure where the 2 is coming from here. Do you guys know? Oh. What's 1 over 2 to the n? What's L over 2 to the n? That would be like, is that the length of a side? One of these rectangles?
It says that the length of the perimeter, L over 2, that's the length of the boundary of R.
Oh, okay. I feel like I can get away with just saying, man, I don't know, I could be wrong, but I feel like I could remove the 2 because epsilon sub n times L over 2n is epsilon n times the length of the perimeter of the nth rectangle. Surely z and z naught, if they're both within the nth rectangle, they're not further than the perimeter apart. So I feel like I can remove that too. Anyway, so, this is what I say, surely. I think that 2 is a typo, all right? All right, so anyway, notice the function g of z, this 2 to be clear, okay? G of z is f of z naught plus f prime of z naught times z minus. Look at this function. Is this function holomorphic with continuous derivative? That function is just linear in z. Notice that the z dependence is just appearing. That is actually an affine function of a complex variable, right? I can just stone cold prove that from limiting process. I could actually do the analysis and completely show that that is holomorphic with continuous derivative because it's just a linear function. There's nothing fancy here. And in fact, you can easily see that the primitive of that, the antiderivative of that is just f of z naught times z plus f prime of z naught times z squared over 2 minus z naught. If you differentiate this big Z, of course you get back to the little g, right? And the derivative is continuous. So without any kind of circular logic here, we can apply Cauchy's integral, not Cauchy, but Cauchy's theorem, or or we can, Cauchy's theorem or Morera's theorem, I don't know. Anyway, certainly the integral around the boundary of rectangle of g of z is 0. Do you guys agree? And I think you can see I'm not assuming the point here either. I'm not using continuity of a derivative of a function that can't be established without this theorem. That's kind of important. We're trying to, well, I guess we already proved that in Morera's theorem, so never mind. Okay, so subtracting this 0 is crucial. So I have this. I subtract 0 by subtracting the g of z, which is basically the, it's the linearization at z naught of f. So, and then what happens? Well, then you've got f of z, you got the difference of f minus f prime times the difference, right? So that is exactly what? That's exactly the thing that differentiability gives us is small. See, because this is, see that? Do you see why that has to be small? You go back up to here, right? So this, if I divide this by z naught, well, I think I'm not using my, sorry, I don't have to go back to here. We went from here, we got this. So I have f of z minus f prime z and z naught. See that right there? That's less than, here's the bound, here's an m, right? So then I use the ML theorem to say that that's less than the bound. Again, I think the 2 is unnecessary. And so the 2, I don't think that 2 should be there. I have L squared epsilon sub n over 4 to the n. And what happens is n goes to infinity there. goes to 0, which establishes what? It's closed. Well, that shows that the integral around the nth rectangle goes to 0, but that's all we need. Well, actually, that's not quite the argument. The integral around the nth rectangle goes to 0 is totally unsurprising, because the nth rectangle is a rectangle which is going to a point, right? I mean, it's getting smaller and smaller and smaller. That's not particularly surprising. We probably could work a lot less hard to get that fact, right? But this is what's interesting, is that the whole rectangle by the Cantor process argument is less than or equal to 4 to the n power times the integral around the modulus of the nth rectangle, right? And we bounded that integral by 2L squared epsilon. Again, I think the 2 doesn't need to be there. L squared e to the n over 4n. So the 4 to the n's cancel, but you're still left with 2L squared e to the n. That 2 was not necessary. And the thing is about epsilon sub n is as n goes to infinity, that goes to 0. If you go back and look at how it was constructed, it's intuitively clear. And there you go. That's Goursat's theorem. So. Which I think if you read Gamelin, you'll pretty quickly see he doesn't really much care for this theorem. I mean, he talks about it with some amount of disdain, which is kind of funny to me. It is true, Goursat's theorem doesn't really help you calculate much of anything, and it is a somewhat technical point, right? That the derivative, if it exists, is automatically continuous for a holomorphic function, right? But, you know, it is still something that's true, and in math we don't like to assume things, we like to show them, right? So.
And so
yeah.
that implies that it's analytic in the sense of power series convergence. Because isn't that the definition of analytic, or am I mixing things up?
Well, a function is analytic, like real analytic, if its Taylor series converges to the function.
Yeah.
So there we need to talk about the convergence of a sequence of functions, and that's what we'll do after the test.
Okay.
We're getting there, but not quite there yet. But we're close. Yeah. But I like to reserve the term analytic for that notion. That's why I haven't been saying analytic up to now. I've been saying holomorphic as a means of communicating. It's complex differentiable at each point. There's some kind of open set on which the function's complex differentiable, right? And then the interesting thing is that even if it's holomorphic on some domain, that doesn't imply that it's integrable, right? I mean, there's something extra if you can get a global antiderivative to the function, right? That says things about integrals being 0 that may not be 0 in general, as we've seen. And yet somehow that's tied to the question of whether or not there is a divergence inside the loop, right? But not just any divergence, apparently a divergence that appears like a linear factor. Because we proved that like 1 over z minus z naught to the third power, to the second power, to the fourth power, integrated around any loop that contains z naught was 0. That was one of our first examples. So just a divergence doesn't make you get a non-trivial loop integral, but somehow like a first order divergence is tied to getting non-trivial integrals around loops. Past the next test, we were mostly talking about exactly the details of that. So there's one last section, which is the partial z versus partial z bar notation. Or I think he called it the Pompey formulas. And so there's something, let me show you a bit of formal nonsense. Partial z is equal to partial x partial z partial x plus partial y partial z partial y, right? And surely partial z bar is partial x partial z bar partial x, right? So what am I doing? I'm just formally mimicking basically the chain rule for operators from Calculus 3. This is how you convert partial derivatives in one coordinate system to another. For example, if you change Laplace's equation from Cartesian to polar coordinates, you might do a calculation like this. Now, how do you relate x and y and z bar? Remember the fundamental formulas? Z is x plus iy, right? Z bar was what? X minus iy. So you can solve those for x and y as well, right? That gives us x is equal to what? You should remember these. This is the real part of z, right? This is the imaginary part of z. If you like the projections onto the real and the imaginary axis respective, these are projections. So you tell me what those partial derivatives are up there. What would they be? Look at this, right? What's partial z there? What would the derivative of this with respect to z be? Partial x, partial z. 1/2, yes. Partial y, partial z? 1/2i, right. So I can rewrite that as 1/2 partial x minus I partial y. And the next one would be what? What's partial z bar is also 1/2 partial x, and then minus 1/2i partial y. Right? So I can factor out the half. What do I have? Now, the reason I say that this is formal nonsense is because z and x, it's like, I mean, it's like a dog and a cat having a baby or something. I mean, it just ain't right. What's that? I probably shouldn't have scratched that itch. Let's see here. And then but I mean, this is a partial derivative of a real coordinate with respect to a complex coordinate. Like, what does that mean? This is not an actual valid chain rule. But this is, in fact, the definition of partial z. And this is, in fact, the definition of partial z bar, right? Now, if you write a definition like that, so these serve as definitions, the question is, is it a reasonable definition? So check this out. What would it mean for partial z bar to be equal to 0? What would this encode? And let's let f be equal to u plus iv as usual. So this is what? 1/2 partial x plus I partial y, u plus iv, or let's just leave it as f for a second here, equal to 0. What's that say? That says 1/2 partial x plus I partial y is equal to 0, right? I can get rid of the half, right? What's that? So if I write that out in terms of real and imaginary components, what's that give you? Give you ux plus ivx plus I times uy plus ivy is equal to 0, which gives you what? Ux minus vy plus I times ux plus uy is equal to 0. In other words, it is the same as ux is equal to vy and ux is, that was a y, and that was a Vx, yeah, sorry. Of course, these are what? Cauchy-Riemann equations. So we can restate the Cauchy-Riemann equations as simply that the derivative of the function with respect to the anti-holomorphic variable, z bar, is equal to 0. So this is just sort of an intuitive idea, but actually a little more than that. So here's some intuition. Holomorphic functions are those of z alone. So for example, if I have f of z is z cubed, holomorphic. It's just a function of z. If I have f of z, and really to be more careful here, I should say f of z bar, because that's what really we're talking about here. If I have f of z bar is equal to z bar, that is not holomorphic. It has a z bar dependence, right? Partial f partial z bar would be what? Z. By the way, you can prove these things. So like partial z bar is what? And what's partial z bar partial z? Partial z, partial z z bar. Guess what? 0, 0, 1, 1. All the things you'd expect. It's just like partial x and partial y. In fact, I would argue this. The best way to understand z and z bar used in this section is that they're really a complex notation for a particular choice of real coordinates in the plane. So when you talk about z and z bar being independent variables, really you're using a complex notation for a function of real variables. But anyway, that may mean I'm out of time. And then some. Oh, okay, well, not too bad. Anyway, I find this to be a very nice kind of end of story because, isn't it? I mean, it's in terms of what holomorphic means, this, for me, operationally is very, very simple, right? Before, we had to do a fair amount of work to see that that was not complex differential anywhere, right? I mean, you actually had to think about it. Here, you just look at it and go, oh, it's got z-bar dependence. Done. And if you look in Gamelin, he has a little bit more on what you can do with these z-bars, but that's about it for us for now, at least. Thanks, Sharon. Now I must go work on your quiz. You turned off? You turned off.
Anything else you want to say?
No? It's good?